Uh, the last part of section 1.8, where we talk about the matrix transformation, uh, two questions here. One is to take uh, a transformation, and do you actually understand that the matrix transformation or the linear transformation is nothing more than matrix multiplication? So for this problem here, find the standard matrix for the operator. When we say operator in terms of the dimensions, what does that mean? The word operator here suggests what? That the vector space of the domain is the same dimension as the vector space for the codomain or the range. Here we're mapping from R3 to R3, right? From the third vector space to, again, the third vector space. So we call that an operator. And otherwise, that operator, if we're going to different dimensions, we call it what it is in the general sense, and that is it's a matrix transformation. So here it says find the standard matrix that represents T, and then compute T of -1, 2, 4 by directly substituting into the equations, and then by matrix multiplication. So understand here that T of A, the transformation, which is the matrix itself, is 3, 4, 3, 5, -1, 2, -1, 1, and -1. Do you see that? Okay. Now you understand that the way this system is written in terms of T being mapped from one space, where here is being mapped back into the same space, these values W are said to be in the range, right? And then the values x sub 1, x sub 2, x sub 3 are said to be in our domain. Now how do we get that? Where we have some transformation with respect to a matrix where we have a vector x, and then somehow we get the output, some vector w. That is to say, we have this matrix 3, 4, 3, 5, -1, 2, -1, 1, -1, times the input vector x sub 1, x sub 2, x sub 3, that gives us the output w sub 1, w sub 2, and w sub 3. So here, this is x, w, and the transformation is this matrix A. So it says, now let's compute T of -1, 2, and 4 directly by just substituting this into the equations. So this implies that we have 3 times -1 plus 5 times 2 minus 4. The second one is 4 times -1 minus 2 plus 4. Then the last one is 3 times negative 1. Just plug in x, y, and z, well, x sub 1, x sub 2, x sub 3 into the matrix here, or to the equation system. Plus 2 times x sub 2, that's 2, then minus 4. So here we have negative 3 and 10, so that gives us 7 minus 4. We have negative 4 plus 4 is 0, so we have left just the negative 2. Here we have the negative 3 and plus 4 minus 4 is negative 3. Now they want to know is when you do that, is that the same as matrix multiplication of the input vector x? It should be the same. So we check. We have 3, 4, 3, 5, negative 1, 2, negative 1, 1, negative 1, times the input vector, negative 2, well, negative 1, 2, and 4. So this is negative 3 and 10 minus 4. Indeed, that gives us the 3. 4 times negative 1 is negative 4. Minus 2 plus 4, negative 2. 3 times negative 1 is negative 3. Plus 4 minus 4, negative 3. Okay, Trey? Are you with me? Okay. Number 6, show that T is a matrix transformation. There are two things that define a matrix transformation, two things that define a linear transformation, right? What are they? James? Yeah, what's that on your cell phone? Okay, look, folks, when you're in my class, make sure that you are with me. If you got something else that you have to do, you go outside, okay? So if you have a computer or cell phone, I don't mind if you have the lecture pulled up on that. That's fine, but anything else, I will not tolerate, all right? If you're sleeping, step out and get you a Coca-Cola or something like that. Wash your face in the bathroom. Come on back. I need your attention because test day is coming up. And after that, you can't say, uh-oh. So this is the time, this is the laboratory right here for us to get this thing worked out. If you have questions, ask me, talk to me. So, again, since Brother James here is the money man, he's checking his paycheck, he should know something about matrix transformation. So, Brother James, the two defining statements for a linear transformation are what? All right. What's your name, sir? Luke knows because he's a genius. He didn't bring any notes, didn't bring any paper or pen, didn't bring a book. So apparently he has everything in his head. So Luke, what are the two defining statements for a linear transformation? Sir, I'm going to sit down while you answer that because I know you got it. Yes, sir. Go ahead. Okay. And he doesn't bring anything to write down. So if we talk about it and whatever it is, how is he going to go home and tell his folk? Does anybody know the two statements? It could be three, but two is what we normally talk about. For a linear or matrix transformation, what are the defining terms? I told you last week that the two statements defines a linear algebra. Didn't I say that last week? Y'all wasn't paying attention. You know, I wonder about that. Even at church, are they listening to us? Two statements that defines a matrix transformation. What are they? Is your favorite color blue? No? Blue jacket, blue book bag. My favorite color is blue. But anyway. Yes? Anybody? Who has the pen? Who gave the pen last week to somebody? They took it with them. Who has the pen now? Buddy? It was given back to me. Okay. What are the two statements? Because I can't go any further. It says, show that T is a matrix transformation. Prove it based on the theorem. Anybody? Give me one of them. I think you're looking at something, man.
I just read a product of two symmetric matrices are symmetric if and only if matrices.
Have nothing to do with that. No, sir. No, sir. That's good digging, though. You know, keep on fishing. Fishing is good, folks. I got to take my little one fishing. Yes, sir.
Could it be that if T represents a matrix and multiply it by X, Y, you get the answer in terms of X and Y?
Nah, we're doing the political game now. You know, we just discuss and talk about stuff. And that's a good thing about mathematics, you know, man. In math, I feel like politics doesn't even work anymore, man. Do you know what they did a long time ago? Just about maybe 60 years ago, when there was some critical issue with China. It was China, Russia, United States, I think England, and it was something with the UN. They were trying to communicate with the scientists where they were dealing with these nuclear warheads and stuff. And when Russia and the United States was going through that period that was called that détente, and they had a critical issue where when they would communicate in the translation, words would get somehow funneled through. You know how in translating a statement, you may have one word in a language that could mean two different things. And so if you get the wrong translation, then the outcome might not be so favorable. Language has tone in it, you know, and so if the tone is not correct, even the words are the same, but if the tone is incorrect, then you get possibly hostility. They were able to overcome the confusion and even to avoid a hostile situation because the matter at hand dealt with nuclear. It wasn't the codes, it was how the equations were all written, these scientific statements. What they were able to do in communicating one with another was to leave the politics outside. And so all these ambassadors and those who spoke for this country and that country, they left them outside. They brought the scientists in, and they asked the scientists and the mathematicians to write down the information that they have in terms of what they're trying to produce. And then, and they all spoke different languages, but just using the formulas and the proofs and all that they had that was given to them, communicate amongst themselves. And they came out of the meeting with a favorable outcome because they were able to talk strictly in terms of mathematics and science with no abridgment to language, because the English language and other languages, certain words could mean something different based on how that person in the other country, how they translated that particular word or phrase. So you say, I like you, I like you. I like you, It could mean something different. You're saying the same thing, That's stupid. That's stupid, man. That second one is like cool, like that's stupid, deaf, kind of, But then the word deaf to somebody, if they don't know what you're talking about, could mean something totally different. But you don't have that in mathematics. It's straight. That's the key. Can't filibuster with this. There are two statements that define linear algebra, my friends. Two statements. You cannot forget this. You need to know this, and you need to pay attention to what I'm saying. And I got the luxury of coming back testing you on this, and I will do it. That's a very harsh statement. But there are two statements that define linear algebra, two statements that define what we call here a matrix transformation. We use that statement here, matrix transformation, but in the scope of things, we're talking about a linear algebra. Two things, that a transformation is said to be, or an equation, if I could say that, is said to be a transformation under vector addition, or matrix addition, and secondly, scalar multiplications. An algebra is called a linear algebra under vector addition and scalar multiplication. Let me scroll up and show you that. It was in this section. The theorem for a linear transformation. This is vector addition. Two vectors, u and v. The transformation of u plus or minus v. Didn't we talk about that? We did. Yeah, I got some writing over there. Is said to be the same thing as the sum of the individual transformations. The transformation is said to be defined with respect to scalar multiplication. So I can say that the transformation of a scalar times a vector is the same thing as the scalar times the transformation. And I gave you an example, you remember that from calculus. I said that all of calculus defines a linear algebra. Talked about that last week. Were y'all here, or was I just talking to the wall? Y'all are hurting my feelings. But TC, I thought we were friends. Mercy, mercy, mercy. Look, folks, you can go through this class and any other class, just going through the motion. Just come in, sit in the class, and, mine is wherever. And then you go home, and right before the test, you just rush, try to study, and try to get the answer, take the test, make it A or B, move on. You've forgotten, or you didn't get the depth and the scope of what was discussed. Because the Bible says that wisdom is the principal thing, therefore get wisdom. But with all thy getting, get, and anybody know what that next word is? Understanding. A lot of folk got wisdom. Not too many have an understanding. That's the key. And when I was a student, my professor would ask a question in class, and he would ask the question, and he'll look at so-and-so, and he'll say, you don't have the answer, do you? And they'll say, what do you mean, Dr. Maryland? He said, because I don't see you writing, because you got to write. Isn't that what the Lord said to John on Patmos? When John was on the Isle of Patmos, he said to him, he said, what thou seest, write. And if you're going to get mathematics, you got to do some writing. Unless you're a genius and you can just look and just hear. And I'm not. I have to do some writing. I have to do a whole lot of writing. And I write it one time, and I put it aside, and I go back and write it again. I put that aside, and I come back and write it again. You see these two things here? That defines the linear transformation. Translation, that defines the linear algebra. That's the whole scope of this entire course. It's confined within these two statements. And we're going to spend a lot of time with these two statements later on. Additivity or homogeneity. But here, this additivity is vector addition. This is scalar multiplication. Right? I don't want to come in class, spend a whole hour talking about stuff, and you don't get it. But if I could spend 10 minutes on something, 5 minutes on something, and you get it, then you have succeeded, and I have too. These are the two things that define a linear transformation. Let's see. So, to show that T is a matrix transformation, we must show vector must show that vector addition holds in scalar multiplication. That is here, that T of U plus V is the same thing as T of U plus T of V, and that T of C times U is equal to C times T of U, where C, this is the how we denote that something is a scalar, where C is an element of the reals, right? So let's pick the two vectors for U and V. Let U equal to x sub 1, y sub 1, and V equal to x sub 2, y sub 2. So we look at T of here, U plus V. Well, according to this is going to be the whatever the first term is times 3 plus the second term. So this is going to be 3 times, and maybe I should write that out. Yeah, I better simplify that. This T of U plus V is, let's look at it. The U is x sub 1 comma y sub 1, and this is plus x sub 2 comma y sub 2. So this is T of x sub 1 plus x sub 2 comma y sub 2, y sub 1 plus y sub 2. Now, this is still in the domain. I haven't done anything but just simplify what this statement of T of U plus V really is. So now this says T of this vector here has to be represented by this form, by this formula. So this, I'm not going to be able to get everything there. So T of x sub 1 plus x sub 2 comma y sub 1 plus y sub 2. This is equal to 3 times the first term. The first term is x sub 1 plus x sub 2. So this is 3 x sub 1 plus 3 x sub 2, plus the second term. And the second term here is y sub 1 plus y sub 2, plus y sub 1 plus y sub 2. That's comma. Now the last part, comma. The first term minus the second term. The first term is x sub 1 plus x sub 2 minus the second term, y sub 1 minus y sub 2. Right? So this is the transformation of the sum. Is that the same thing as the sum of the transformations? So we look at t of u. T of u, well, u is said to be x sub 1 comma y sub 1. So this is, according to the formula, this is 3 times the first guy, x sub 1, plus the second guy, which is y sub 1, comma, the first term minus the second term, x sub 1 minus y sub 1. Now we have to pull up t of v. Right? This is t of x sub 2 comma y sub 2. So this is 3 times the first term, x sub 2, plus the second, y sub 2, comma, the first term minus the second term. Now we have to see if t of u plus v, is that the same thing as t of u plus t of v? Basically, we add t of u plus t of v, add the results to see if that equals the result right here. See if I can push this down. So t of u plus t of v is equal to, we're going to add these terms together. So this is 3x sub 1 plus, I'm going to connect that, this is plus 3x sub 2 plus, just associating, y sub 1 plus y sub 2, comma, x sub 1 plus x sub 2 minus y sub 1 minus y sub 2. Is that the same thing as t of u plus v? Well, let's see, we got t of u plus v. We got that to be 3x sub 1 plus 3x sub 2 plus y sub 1 plus y sub 2. So good so far, comma, up here we got x sub 1 plus x sub 2 minus y sub 1 minus y sub 2. Well, they're the same thing. So you conclude that that was the first part. The t of u plus v is the same thing as t of u plus t of v. So now, what about the second part? Show t of c times u. Is that the same thing as c times t of u? Well, look at the left side, which is t of cu. Well, this is t of c x sub 1 comma c y sub 1. Now that equals to, according to the formula, it's 3 times the first term plus the second. So this becomes 3 times the first term, which is c x sub 1 plus the second plus c y sub 1, comma, the first term minus the second, c x sub 1 minus c y sub 1. So the right side is C times T of U. This is C times T of X sub 1 comma Y sub 1. This is C out in the front times 3 X sub 1 plus Y sub 1 comma X sub 1 minus Y sub 1. Now, if you go back to the first term, here, the left side, you can factor out that C, which is common in these two positions, common there, and we'll get that. So it's a period. Notice that T of CU, which is what we have here, which is 3C X sub 1 plus C Y sub 1 comma C X sub 1 minus C Y sub 1 is equal to C times 3X sub 1 plus Y sub 1 comma X sub 1 minus Y sub 1. That's equal to C times T of U. So T is a matrix transformation. Right? Write that here. Yes, sir. Homogeneity. Yes. Yep. In a later chapter, we would have to show that a space is a vector space. There are 10 axioms that we have to show. 10. And the first 5 deal with vector addition, and the second 5 deal with matrix multiplication. So we break down vector addition into commutativity, associativity. We break down matrix multiplication of a scalar into association, commutativity, distributive function or property for vectors, distributive property for scalars. So everything that you did or maybe skipped over the first week in algebra, we have to actually prove now to make sure it's well defined. That's what we do here. So T is indeed a matrix transformation. The second example, we will show that T is not a matrix transformation, or that T is not linear. So I want to give an example for each. T is indeed a matrix transformation. Him on down there. Show that T is not a matrix transformation. Well, what we do to show that something is not is that we assume that it is, and so we still go through the same process. We look at vector addition to see if that holds, and also to see if scalar multiplication holds as well. There are certain problems later on where they will say, if there are 10 axioms that you have to prove, you would think, I would think, okay, if one of them fails, let me just find that one and say this one fails and I'm done. Well, I think in the main scope of things, that's acceptable. But there will be problems where they would ask you to show all 10. So you may have like 8 of them that's satisfied and only 2 of them that fails, but you still show all 10. Here, show that T is not a matrix transformation. If the first one fails, then I would think, we stop right there. But what I would do, and on the test, if I give you a problem like number 7, and I ask you to show that T is not a matrix transformation, it's okay for you to show just one. If it fails with vector addition, then you're done. Okay? Because it fails, it's going to fail, right? I will show both of them to show you where both of these guys fail and why. Okay. let u equal to x sub 1 comma y sub 1 and v equals to x sub 2 comma y sub 2. Excuse me. So t of u plus v is equal to t of here, the u is x sub 1 comma y sub 1 here plus v, which is x sub 2 comma y sub 2. That's equal to t of x sub 1 plus x sub 2 comma y sub 1 plus y sub 2. Just want to simplify it. Now we write what it is based on the formula up here. This formula says take the first term, you square it, comma, just write the second term as it is. So here, this is x sub 1 plus x sub 2 to be squared, comma, y sub 1 plus y sub 2. That's a big one. Now, what about t of u plus t of v? This is t of x sub 1 comma y sub 1 plus t of x sub 2 comma y sub 2. Well, the t of x sub 1 comma y sub 1 is simply x sub 1 squared comma y sub 1. And this is plus here the t of x sub 2 comma y sub 2 becomes x sub 2 squared comma y sub 2. And we add them together, you get x sub 1 squared plus x sub 2 squared comma y sub 1 plus y sub 2. This is not equal to t of u plus v, right? Because t of u plus v is equal to, see, this x sub 1 plus x sub 2 to be squared is not the same thing as x sub 1 squared plus x sub 2 squared, right? They're different. Now I have to simplify that for my math 100 students, so I better go ahead and simplify it also today. So, because t of u plus v, if you write that out, this is x sub 1 squared plus 2 x sub 1 x sub 2 plus x sub 2 squared, right? Comma y sub 1 plus y sub 2. This is not the same as that. That part fails. So on the test, if I ask you that, if you get one part that fails, then you say, hey, it's not a transformation, and you're done, right? You can even show the second one only if it fails, and you know, which is quicker to show. Show the t of cu is equal, well, question mark, we don't know. So here, t of cu is equal to t of, I'm going to put that scalar times here, the u, so this is c x sub 1 comma c y sub 1. So this is equal to, this says the first term squared, so this is c x sub 1, just write it out. This is c squared x sub 1 to be squared, comma, c y sub 1. Now what about c times t of u? This is c times t of x sub 1, comma, y sub 1. This is c times, this is the first term squared, comma, the second term. Right? You see that they're not the same? T of CU is not the same thing as C T of U? Look here. This is C squared X squared, comma, C y sub 1. It's not the same thing as, you can put this C inside if you want to, just to see that. This is C X sub 1 squared, comma, C y sub 1. That first one has the C squared in there. This is just C. So T of CU is not equal to C times T of U. Thus, T is not a matrix transformation. Okay, any questions there? Yes, sir?
If one fails, do they all fail?
No, not necessarily. Yeah. And we'll get into more detail, I think it's chapter 4, where we talk about a space where all these terms are supposed to be inclusive of a big space, and to show that the space has a well-defined skeleton, so that you can put whatever skin you on the skeleton if you want, but if the skeleton has a flaw in it, then the whole system breaks down. In that, it's possible to have maybe 3 or 4 of the axioms to hold, and maybe 1 or 2 of them fail. But it doesn't really matter, because if only one fails, then it's not exactly. Yep. Yes, sir. Good. Any other questions? Okay. Let's look at the next section. Let me close this out.